Okay. Just as a warm-up exercise, I'd like you to try to prove the following. So prove that if Fn are all continuous and they converge uniformly to some F. So Fn converge uniformly to some F. Then that F is also continuous. Okay, so maybe just to make it concrete, let's say that these guys are continuous on an interval 0, 1. So all these guys are on 0, 1, and they go into R, just to make it concrete. So this is, a consequence of the theorem that we had last time, but I want you to just prove it directly from definition of continuity and the definition of uniform convergence. If you can do this, then you understand uniform convergence and continuity. Okay, can anybody give an idea? Anybody give an idea of how this should work? Like what's the idea? What do we have to show? Remember, we want to show that given any epsilon, that there's a delta neighborhood of x, right? There's a delta neighborhood of x in which the f, right, the limit function doesn't vary outside of this epsilon, outside of epsilon, right? Okay, right. And what do we have? We have that that the f sub n converge to f uniformly. Right? These guys converge to f uniformly. In other words, if we have a tube, if we have any tube around the graph of f, then we can find an n past which all of these guys lie within that tube. Okay, right. And we also know that each of the f sub n is continuous themselves, right? Each one individually is continuous, right? So if we have fx and we are looking at fn, right? So suppose we have some fn, right? Any of the fn is going to have the property that, right, if this is fnx, then fn plus epsilon prime, fn minus epsilon prime, we can find some delta neighborhood in which the fn satisfies that, right? In which the fn doesn't vary by more than the epsilon prime. Okay. Okay. So what's the idea? Anybody have a sort of intuitive way of describing it? Yeah.
Triangle inequality.
Triangle inequality. Yeah. Triangle inequality.
Split up.
It's true.
Like you can split up. Basically, you can find delta. For every point within that delta, you can split the distance between ft and absolute value of ft minus fx, split it into 3 small distances which we have control with. I can just explain.
Sure. Okay, so you say, okay, well, look, let's take some delta neighborhood, right? Or let's take some t here. Okay, let's take some t here. And you're saying, well, look, if we look at the difference between f of x and f of t, then
You can split
into what?
You first split into absolute value of ft minus fnx plus absolute value of fnx minus fx. Is that correct? I think so. Right?
You probably want to use a t here, right? This would be this first guy.
You can split the first one again into 2.
Okay, sure. Okay, so you're gonna split this thing into.
Yeah.
Okay.
So you can split it into 2.
So you're gonna say
ft
minus
fnt plus fnt minus fnx. Then you have the last one. Yeah. Then each of the 3 distances you can control them with the conditions we have.
Okay.
Control them within 1/3 epsilon. I think that's how I approach it. Maybe it's wrong, but that's
no, that's right. That's right. Yeah. So maybe Lan, that's what you were saying.
No,
So.
I think the way I was describing it choose a different one to triangulate that, but then I don't think I was very good at describing the mechanical requirements.
I think we have the same.
Okay, good. I'm sorry that, it's a little tricky to do it to understand other people. But, okay, so yeah, so you say, okay, well, look, we're trying to show that, we can make this small, right? We're trying to show that we can make this small. We know that since the f of s of n converge to f uniformly, right? We know that there exists some n such that if n exceeds n, then f of t minus f n t is smaller than epsilon over 3 for all t in 0, 1. For all t in 0, 1, that's true. Right? Including x, right? So each of this, this is going to be smaller than epsilon over 3, and this is going to be smaller than epsilon over 3. Okay. So, right? So just choose any n not bigger than n, right? Choose any n not bigger than n, and we see that, so this is going to be less than epsilon over 3, that's going to be less than epsilon over 3. Since f n naught is continuous, we know that there's a delta neighborhood, right? There's a delta neighborhood such that in the delta neighborhood of x, we have fnt minus fnx is smaller than epsilon over 3, right? Such that for t in the delta neighborhood of x, we have that, right? And so in that delta neighborhood of x, right, we have fx minus ft is smaller than epsilon. Okay. Okay. Right. Is that clear? Okay. So if you understand this, then you pretty much understand uniform convergence. Another way of seeing it is to say, well, look, so the picture is this, right? You choose your n such that it's past this capital N. So that means that the Fn lies within the epsilon over 3 tube of F, right? But that's the same thing as saying that F lies in the epsilon 3 tube of Fn, right? You could conversely say that's true, right? So here's my Fn, and I know that F, whatever it is, must lie in the epsilon over 3 tube, right? So F must be somewhere in here. I don't know what it is, but it lies in this epsilon over 3 tube, right? Well, if you lie within the epsilon over 3 tube here, well, choose the neighborhood where f sub n varies by less than epsilon over 3. Right? If f sub n varies by less than f over 3 here, and f sub x varies by less than epsilon over 3 from f sub n, well then f itself cannot vary by more than epsilon. Right? Does that make sense? Right. So that's the idea. You say, well, look, f sub n is continuous. F sub n is continuous. So I can find a place where it doesn't move that much, right? And I know that f is close to that. Well, then f can't move that much either, right? That's the basic idea. And then you just flesh it out here, okay? So as long as you get the intuition first, right, then you believe what you're saying, and then you write it down. Then you make up something that justifies it. Okay. You have to come to the point where you believe what you're saying first. Yeah. When I was in graduate school, there was another graduate student who said, we should be able to prove anything that we say. Like true or false. We should be just able to prove whatever we think, whatever we come up with. Which is, I think, not exactly the right attitude, but it's sort of the right attitude. Okay. So let's go back. So different perspective. Alternate perspective of uniform convergence. Alternate perspective of uniform convergence. Okay. So let X be a metric space. Okay, let C of X denote the functions, the complex valued functions on X, where F is continuous and bounded. So continuous and bounded functions on this metric space, and that's the first definition. The second definition is we define for functions in this space, we're going to define a norm by taking the supremum of all, the magnitudes of all possible values. Okay. So define the norm of the function to be the supremum of the magnitudes. Okay. And define for two functions. Define the distance between them, the distance between f and g, as the norm of the difference. Okay. This is sort of the usual thing to do.
Professor?
Yes?
How do you write the notation for the function? For the first one?
F?
That's C.
Like all three of them. What is that?
C? That's a C.
Okay.
That's okay. It's a C.
It's cursive.
C. C.
You know what the LaTeX?
What?
Like the
I think it's math. You can just write this math scra. C. Yeah. Math script. Is that what you wanted? You needed the LaTeX.
Yeah, instead of writing that, I'm just gonna write every time.
Yeah, that might be faster. Yeah. Now, if you take the Fourier analysis class eventually, you're gonna have to write C. Right? There'll be a lot of zetas. There'll be zetas, and there'll be C's. Okay, so you have to be able to write them. Put the necessary number of loops.
That's epsilon.
That's not epsilon. Epsilon is this.
The one that we
Anyway.
have is var epsilon.
What?
Epsilon, yeah.
Yeah.
Var epsilon?
Yeah, the one that we use for like the other epsilon is var epsilon. This one is not.
Okay. In any case, just when you get to it, zeta is easy, and then C you can put however many loops. As long as it's distinguished from zeta, it doesn't matter. Okay, let's get to it. Okay, so you have a metric space, you have the continuous functions, continuous and bounded functions, right? And you define this norm. It's just the supremum, the least upper bound of the greatest value, right? Of the magnitude of the greatest values. Yes.
For number 2, is it saying
For f in this thing,
okay.
let the magnitude, let the norm be defined as the supremum of the moduli of the values. Sorry. This one. Okay, so it's an exercise, I'm not going to do it, that if you have C and you have this norm, this is a metric space. Okay, so that is that this distance here actually gives you a metric. So let's think, what does Fn converging to F in this metric mean? What does Fn converging to F in this metric mean? Right, that the limit, you've got these functions, and their limit is F, right? Right. That would mean that you can make this distance as small as you want, right? You can make this distance as small as you want, right? That the limit of the distance, right? The limit of the distance is 0 as, sorry. That the limit of the distance is 0, right? Well, what does that mean? That means that given any epsilon, right, there exists an n such that if n is bigger than n, then the supremum of fnx minus f of x is less than epsilon, right, as x ranges over your set x. So what is that? Right. The supremum of this thing is less than epsilon. In other words, that Fn x minus f of x is less than epsilon for all x and x. Well, what is that? That's uniform convergence, right? Right? So this is just another way of looking at, you should know the answer because I put this thing at the beginning, right? Alternate perspective of uniform convergence. Right? This is uniform convergence. Okay, so, right, you can define a metric on this space, and convergence with respect to this metric is the same thing as what we've been calling uniform convergence. Yes?
Why? Is there any reason why we're particularly looking at the square root of c?
Square root of c.
The function square root of c.
Say
Isn't that what you said? Math square root c?
No, it's.
No, sorry. This is, somebody wanted to know the LaTeX LaTeX code for this fancy c.
Okay.
Right? So, yeah. Okay, so that's that. And let's observe that theorem that, in fact, if we take the continuous functions and we put this norm on it, we put this metric on it, then in fact this is a complete metric space. Okay. So to show that, we need to show that every Cauchy sequence converges, right? So proof, we want to show that if f sub n is Cauchy, then f sub n converges to some f in the space, right? That's what being complete means, right? Every Cauchy sequence should converge to something in the space. Okay, so this is pretty straightforward. You say, well, look, Fn Cauchy means that, just the definition of Cauchy, right, for all epsilon greater than 0, there exists n such that n and n exceeding n implies that the distance between Fn and Fn is less than epsilon. This is the Cauchy criterion. This is the same thing as the Cauchy criterion for uniform convergence. Okay. Right, so this is the same thing as the Cauchy criterion for uniform convergence. So there exists an F such that Fn converges to F uniformly. Right. What we said, just what we said before. This is uniform convergence, so this is uniform convergence. Right? So there's going to be somebody that you converge to, and the only thing is to show that this guy is in the space, right? Is F in the space? Is F in the space? Well, you just need to answer if it's continuous and if it's bounded, right? Is it continuous? Yes, by the previous theorem, the thing that you all proved at the beginning, right? Continuous functions that uniformly converge to a continuous function. Right? Yes, by the exercise. So F is continuous by the exercise, right? And F is bounded. Why is F bounded?
Each guy in the sequence.
Each guy in the sequence is bounded.
Uniformly converged.
Yeah, so each guy in the sequence is bounded, and you have uniform convergence, right? So you can use what I said before, right? That you can get within epsilon of this guy by a bounded guy, right? So you can get within epsilon, right? You can choose, right? We can choose n such that the distance between Fn and x and f is smaller than 1, say. Okay, but this guy is bounded, right? This is bounded, right? This guy is bounded, and so that will imply that f is also bounded. So that's, you should write it out more properly, but that's basically the reason. Okay. Okay, is that clear? Is that clear? Anybody want to see that more? Okay. Okay. So okay. So a little bit of a digression now. So let me give you a brief introduction to integrable functions, into integration. So a brief introduction to integration. So one thing that uniform convergence works nicely with is integration. But we skipped the chapter on integration. So let me just give you the parts that you need. Okay. Let me give you just like the concise introduction. Okay, so okay, so given an interval, this is pretty straightforward stuff. So I hope you like it. It's maybe easier to grasp than some of the stuff we've been doing recently. So given an interval AB in the real numbers, and f on that interval, a bounded function, then we have a bunch of definitions. So we're going to define what it means to be Riemann integrable. Okay. What kind of functions do we call integrable? The definition is a little bit involved. some of you have probably seen this before. Okay, so the first thing we do is we introduce a set of points x0, x1 through xn. And these points lie in AB. Okay. So P is called a partition of AB if x0 is less than x1, is less than x2, is less than xn, and the first guy is A and the last guy is B. Okay, so all this is saying is that you have A, B, and you have a bunch of points that are increasing, x0, x1, and the first guy is A and the last guy is B. Okay, if that happens, then you call this collection of points a partition. Okay. Part 2, we introduce a notation. Let capital MI denote the supremum of f of x as x ranges over the ith subinterval. Okay, so we've got these points, right? We look at the ith interval, right? We look at the ith interval and we take the supremum of your function over that. So maybe your function is pretty straightforward. It looks like this, right? So the supremum value would be called mi. The minimum value, the infimum would be called little mi. So little mi is defined as the infimum of f of x over the ith interval. Delta xi is defined as the length of the ith interval xi minus 1. And we define UPF as the sum of mi delta xi as I ranges from 1 to n. So you've seen this before, I'm sure. Right, you have some interval AB, you have some partition, right? You have some function, and on the first interval, you take the greatest value, right? You take the greatest value, you multiply that by the width, right? You take, on the second interval, you take the greatest value, multiply that by the width, greatest value, multiply that by the width, greatest value, multiply that by the width, and you call that the upper sum, right? The upper sum of this function over this partition. So this is the upper sum of f on p, right? And of course you've got the lower sum, that will be summation little mi. Okay. The important definition, number 3, are the so-called upper and lower Riemann integrals. So the upper Riemann integral is written like this. The integral from a to b with a bar above the integral sign. Okay. And that is defined as the infimum of the upper sums. Okay. The infimum of the upper sums as over all partitions. Okay, that's the funny thing. Over all partitions, right? Over all possible partitions. Okay, so you take the the lower bound of the upper sums. The greatest lower bound of the upper sums. And of course, the lower Riemann integral will be the opposite. Right? AB lower integral is going to be the supremum of the lower sums. Yeah.
Did you put that dash?
That dash indicates whether it's upper or lower. So the dash above the integral sign,
Okay.
the dash below the integral sign. Upper integral, lower integral. Okay, and so here is finally we can actually define, we can finish up the definition. So, part 4, if the lower integral, thanks, see. If the lower integral and the upper Riemann integral are the same, we say that f is Riemann integrable. On AB. So if the lower integral and the upper integral are the same, then we write, right, suppose they equal some common value L, then we write this integral equals that value L. So that value would be the Riemann integral. Yeah, Abel.
Is it for some choice of partition or for every choice of partition?
So, right, so this upper integral is the infimum over all partitions.
Oh,
The
okay.
infimum over all possible partitions, right? So you take all possible partitions and take the upper sums over them. And you say, okay, I'm going to take the lower bound, the greatest lower bound of all those upper sums, right? You sort of see what happens, right? As your partition becomes finer, well, your upper sum becomes smaller, right? If I threw in more points, then the maximums would only decrease on each, right? The maximums would decrease, and then so I get a smaller, more accurate number, right? And so you're taking right? And similarly, the other guys are only going to become larger, right? As I make the partition more and more fine.
So that's why you take the infimum of the
That's
upper
right.
integral and then...
And you take the supremum of the lowers. Okay. And if it turns out that those things are equal, then we call the function Riemann integrable. Okay. It's it's not a hard thing to show that any continuous function will be Riemann integrable, or any function with a finite number of discontinuities will be Riemann integrable. Let me give you a non-example. So an example of a function that's not Riemann integrable. Okay, and that would be the indicator function, a characteristic function of t. Right? Because your function looks like this, right? Let's say we're doing it on some interval AB. Let's say it's 0, 1. Right? Suppose we're on 0, 1, and we have the function that is 1 on the rationals, 0 on the irrationals. Okay. Well, then what's going to happen? What's going to be the upper sum for any partition? Right? If I take any partition, and I take the upper sum, I take the maximum, I take the supremum of values, right? Well, that's always going to be 1, right? So I'm always going to, my capital M is always going to be 1. And then I'm going to multiply by the width, right? So no matter what happens, UPF is going to be 1.
Why is the upper sum always going to be 1?
Well, what's capital M? Capital M is the supremum of F, right? Well, my function is 1 on the rationals and 0 on the irrationals, right? So I'm always going to have values that are irrational here. So I'm always going to have values of 1, outputs of 1, right? Okay. And similarly, my lower sum is always going to be 0, right? Then when I take the upper Riemann sum, well, I get the infimums of 1. Well, that's going to be 1. I get the supremums of 0. That's 0, right? And so no matter what happens, this is going to be 1 and this is going to be 0, right? So this is not a Riemann integrable function. Okay. Okay. Now when you do the Lebesgue integral, you'll say, well, this Q is actually a small set because it's a countable set. Okay, it's a countable set, and so we can cover it with arbitrarily small amount of material. So this Q actually doesn't contribute anything, and the integral should be 0, right? Because basically, 100% of the time the value is 0, right? Excluding Q, which is a tiny set. The width of Q, the measure, what's called the measure of Q, is 0. So this is not Riemann integrable, but it is what's called Lebesgue integrable.
Does that mean that Riemann integrable functions are subsets of Lebesgue integrable functions?
Yeah. Yeah, the Lebesgue integral is like the superior integral. Now, one of my uncles is in math, and he said that the Lebesgue integral should be properly called the Young integral. Yeah, his arguments over, priority. So maybe that's what it should be. But anyway. Okay. I think we're going to make it, but let's keep on going. Okay, so a bunch of simple observations. So remember that F was bounded, right? F was bounded. So F lies between some minimum and some maximum, little m and big M. So a dumb observation, for every partition, we know that the upper partition is smaller than m times the width of the interval, and we know that the lower partition is greater than little m times the width of the interval. Not surprising. Right. B, right, little m, big M. Right. Little m, big M. Right. Not surprising. Okay. More interesting, number 2, let P and P prime, P and P star both be partitions of some interval AB. If P star contains P, right? If all the points that are in P star, we call P star a refinement of P. If so that's part A of the definition. Part B of the definition is that if P1 and P2 are partitions of AB, then we call P1 union P2 the common refinement. The common refinement of P1 and P2. So it just means that you throw in all the points, right? So P1 has some points, right? P2 has some points, right? And then the union would be you just take all these points and you use that as a partition. Okay. Last observation, if P star is a refinement of P, then the lower sum based on P and the lower sum based on P star, well, what's the relation?
Lies inside. Is it a subset? Because P star is bigger than P.
Well, remember, this is a number, right? So this is the lower sum, right? You take the minimums over, right? You take the minimums over each interval, right? You take the minimums over each interval. So now we're taking
Less than equal to.
less than equal to.
Yeah.
So of course it's going to get bigger, right? And for the upper sums, the opposite will happen. Okay, let's stop there. Let's stop there.